All right, welcome to another video in the Wild Networking series. We're going to keep reading the Cisco Campus LAN WAN Design Guide. We're on to the wireless section now, so we're going to be reading about AP site tag considerations. Cisco Catalyst 9800 series wireless LAN controllers have a multi-process architecture. Multiple wireless network controller processes, WNCD, run within a single Cisco Catalyst 9800 platform. The number of WNCD instances varies from platform to platform. APs and wireless clients are load balanced across the WNCD instances for better scale and performance. In recent software releases, APs are load balanced across the WNCD instances based upon the site tag applied to the AP, which stands for access point. I'm not sure what WNCD. Oh, wireless network controller processes. Okay, which stands for WNCD. If I guess D stands for daemon, because daemon sometimes I think is interchangeable with the term processes. If the default site tag is used, APs are load balanced across the WNCD wireless network controller processes instances in a round robin fashion. Roaming and fast roaming work across site tags. However, 802.11k assisted roaming, 802.11v BSS transition, coverage hole detection CHD, and other proximity-based features are managed within multiple WNCD instances. Therefore, a best practice design recommendation is to configure custom site tags and not use the default site tag. For best performance, use a custom site tag to group APs within a roaming domain. Also, a best practice is to limit the maximum number of APs per site tag to 400 APs. The following are recommendations based on specific deployments. If the deployment has a building with more than 400 APs, consider splitting the building into two parts from site tag perspective. Each part should have its own custom site tag with less than 400 APs. So here's a single building with more than 400 APs, and here's multiple buildings with more than 400 APs. So in a single building with 400 APs, more than 400 APs, you're going to want to divide up the building. If the deployment has a roaming domain that spans across multiple, as is described here, if the deployment has a building with more than 400 APs, consider splitting the building into two parts from site tag perspective. Each part should have its own custom site tag with less than 400 APs. So you're going to make sure that you want to make sure that the tags have fewer than 400 APs, and if you have a single building, you're going to want to basically treat it as if you have multiple buildings. If the deployment has a roaming domain that spans across multiple buildings with more than 400 APs, consider configuring a site tag per building. Multiple buildings with more than 400 APs, so now we have a site tag for each building. If the deployment has multiple buildings with less than 400 APs, consider configuring a single custom site tag. Don't use the default site tag. So a little bit unclear here. I'm not sure if they mean that across multiple buildings there are more than 400, or if they mean per building, each building has more than 400. Likewise here, I'm not sure if they mean each building has less than 400, or in aggregate, the total of APs across all buildings is 400. I'm very unclear about that. But I think it's in total aggregate. When deploying Cisco FlexConnect, set the site tag to be a non-local site within the Cisco Catalyst 9800 configuration. When the local site is disabled, the Site tag is equivalent to a Cisco Flex Connect group in classic Cisco Air OS wireless controllers. So this is site tags for Cisco Flex Connect APs. We've got site tag 1 for all 3 branches. There is a limit of 100 APs per Cisco Flex Connect site tag for seamless roaming. Roaming across site tags for Cisco Flex Connect APs results in a client full re-authentication. High availability. As more devices with critical functions move to the wireless medium, high availability of the wireless infrastructure is becoming increasingly important. Real-time audio, video, and text communication relies on the corporate wireless network, and the expectation of zero downtime is becoming the norm. The negative impacts of wireless network outages are just as impactful as outages of the wired network. Well, that seems pretty duh. Implementing high availability within the wireless infrastructure involves multiple components and functionality deployed throughout the overall network infrastructure, which itself must be designed for high availability. This section discusses high availability specific to the implementation of wireless controller platforms. Platform level redundancy refers to the ability to maintain wireless service when connectivity to one or more physical LAN controller platforms within a site is lost. Designing for high availability must also consider the entire life cycle of the deployment, including the need for updates and upgrades on the network. This section also discusses the use of software maintenance upgrades, SMUs, for wireless controller fixes and updates, AP service packs, APSPS, for AP fixes and updates, and AP device packs for support for new AP models. The methods of high availability discussed within this design guide, available with releases of Cisco iOS-XE 17.1 and higher, are as follows. So we've got high availability SSO. I'm not sure what that stands for. I thought it was like single sign-on. What does SSO stand for? Yeah, single sign-on. N+1 high availability. Not sure what that means either. Oh, it looks like they're going to go through each of these and explain them. So let's just read through the list, and then we'll read through the explanations of each item in the list. WLAN controller link aggregation, wireless controller patches using software maintenance updates, SMUs, AP patches using AP service packs, AP SBS, support for new AP models using AP device packs, AP DPS. High availability stateful switchover, HASSO. Cisco wireless LAN controllers support AP stateful switchover and client stateful switchover. These two features are collectively referred to as HASSO. For both simplicity and efficacy, HASSO is the preferred option for providing high availability. Cisco wireless deployments can improve the availability of the wireless network with controller recovery times in the sub-second range during a WLAN controller disruption. The configuration and software upgrades of the primary WLAN controller are automatically synchronized to the resilient standby WLAN controller. N+1 high availability. You can use the N+1 HA high availability architecture in order to provide redundancy for WLAN controllers within a single site or across geographically separate sites with lower overall cost of deployment. It is often deployed along with the Cisco Flex Connect architecture in order to provide high availability across data centers for remote branches. You can use a single backup WLAN controller in order to provide backup for multiple primary WLAN controllers. HA-SSO functionality is not supported for N+1 HA. When the primary controller fails, the AP CAPWAP state machine is restarted. With N+1 HA, WLAN controllers are independent of each other and do not share configuration or IP addresses on any of their interfaces. Each WLC must be managed separately, can run different hardware, and can be deployed in different data centers across the WLAN link. It is recommended, but not required, that you run the same software version across WLCs used for N+1 HA in order to reduce downtime as the APs establish CAPWAP sessions to the backup controllers. You can configure APs with a priority using N+1 HA. APs with high priority on the primary controller always connect first to the backup controller, even if they must push out low priority APs. When a primary WLC resumes operation, the APs fall back from the backup WLC to the primary WLC automatically if the AP backup option is enabled. I gotta take a quick break, I'll be right back. Alright, I'm back. This is the WLAN controller link aggregation section. Cisco wireless controller appliances have multiple physical Ethernet ports. In typical deployments, one or more WLANs/service set identifiers, SSIDs, are mapped to a VLAN interface, which is then mapped to a physical port. In a centralized design, wireless traffic is backhauled across the network infrastructure and terminated on the physical ports. With the use of a single physical port per WLAN, the throughput of each WLAN is limited to the throughput of the port. Therefore, an alternative is to deploy link aggregation, LAG, across the distribution system ports, bundling them into a single high-speed interface. When LAG is enabled, the wireless controller dynamically manages port redundancy and load balances APs transparently. If any of the controller ports fail, traffic is automatically migrated to one of the other ports. If at least one controller port is functioning, the wireless controller continues to operate. APs remain connected to the network, and wireless clients continue to send and receive data. Preferred redundancy. Cisco Catalyst 9800 high availability SSO pair connected to redundant single logical switch. LAG requires an Ether channel port group to be configured on the attached Cisco Catalyst switch. The Ether channel port group can be configured across multiple line cards on the switch or across switches in a Cisco Stackwise virtual configuration for additional redundancy. When configured across switches, the group is referred to as a multi-chassis Ethernet channel, MEC. The Ether channel is configured using 802.1q trunk encapsulation to carry multiple VLANs from the controllers into the switching domain. The following figure shows an example of wireless controller link aggregation in a high availability configuration to a Cisco Stackwise virtual pair. Similar connectivity is used when connecting to a distribution switch stack. Preferred redundancy for controller HA-SSO pair. So this is a Stackwise virtual pair. It's as if this was one switch. So these links here are as if they were one link. This is a single AG group per controller connected to multiple switches across a Catalyst Stackwise virtual pair, BSS pair, or switch stack. So you can see we've got 4 links we can use for that, so we can use a lot of bandwidth a lot of extra bandwidth doing this. And not only that, now you have active and a standby. Anything goes wrong with your active, it'll immediately go over to your standby. Now this is an RP port. I guess I'm not sure. Yeah, it's kind of not clicking for me, but let's just keep on going. Spreading the ports from the active and standby WLCs across both switches within the Cisco Stackwise virtual pair is the recommended design. This design minimizes the traffic that crosses the virtual switch link between the Cisco Catalyst switches in the Cisco Stackwise virtual pair during normal non-failure operation. Because both the active and standby WLCs have ports connected to both switches, this design also avoids a switchover from the active WLC to the standby WLC in the event of a switch failure within the pair. However, in the event of a switch failure within the pair, the number of ports connected to the active WLC is reduced by half. You choose a switching platform with appropriate resources to support ARP and MAC address table entries from the wireless controller for the deployed environment. Note Catalyst 9800 wireless controllers support PAGP and LACP as of iOS XE 17.1 and higher. Preferred redundancy - single Cisco Catalyst 9800 controller connected to redundant single logical switch. If you are only connecting a single Cisco Catalyst 9800 controller to the wired LAN, such as for an N+1 controller deployments, connect the single controller physical ports spread across redundant Cisco Catalyst switches in a Cisco Stackwise virtual pair, switch stack, or separate line cards in a highly redundant modular chassis. This is the preferred redundancy for a single controller. We've got a Stackwise pair, basically one switch, and then we've got L2 port channel. And really important, even though this is operating as one switch, you've got to make sure to connect it across both switches. Otherwise, you don't have that redundancy if one of the switches fails. The trunk configuration and switching platform choices from the previous design also apply here. Wireless controller patches using software maintenance updates, SMUs. An SMU is a software package that can be installed on a wireless controller to provide a patch fix for bugs or security resolution to an already released image. Cisco Catalyst 9800 series controllers support two types of SMUs, hot patching and cold patching. A hot patch does not need a system reload, meaning that clients and APs will not be affected when applying the hot patch. When the oh no. Okay, so this is going to be one of, this is going to be one of these videos where a lot of it, my audio went out. They call it YouTube poop. Sorry, this is going to be YouTube poop. My headphones went out. They've been doing that for some reason. I've got them on a charging brick, so I thought they'd be fine, but they just like deactivate themselves randomly. They just did that again. Okay, so am I good now? Yeah, I'm good now. So yeah, it just randomly deactivates itself. I'm not sure why that happens. It's hooked up to a power brick, so it should have power. I don't understand. Um, but that's, yeah, as I said, this is just going to be a junk video. Things weren't kind of clicking with me anyway. So I'm just going to try to finish this section here. Hopefully my um, headphones will behave, and then I'll end the video. So wireless controller patches using software maintenance updates of SMUs. An SMU is a software package that can be installed on a wireless controller to provide a patch fix for bugs or security resolution to an already released image. Cisco Catalyst 9800 series controllers support two types of SMUs: hot patching and cold patching. A hot patch does not need a system reload, meaning that clients and APs will not be affected when applying a hot patch. When the wireless controller is part of an HA-SSO pair, the SMU activation applies to both the active and standby controllers. A hot patch does not require, a cold patch does require a system reload. However, in an HA-SSO pair, the system will first install the SMU on the standby controller and reload it. Once the standby finishes reloading, the active controller will reload. When this happens, a switchover occurs and the standby controller becomes the new active controller. The new active controller takes over all AP and client sessions. Then the new standby controller, previously the active controller, is updated. Throughout this update, AP and client sessions remain up. Note, SMUs are only released on long-lived Cisco IOS XE extended maintenance releases. Okay, so it'd be nice if I could get down to this multicast support section. I'm going to try to do that. AP patches using access point service packs, AP SPS. Cisco Catalyst 9800 series wireless controllers support rolling out critical AP bug fixes using AP SPS. AP SP rollout can be based upon sites, with the fix pre-downloaded and rolled out to only affected AP models. With rolling AP upgrade, AP upgrades can be staggered to ensure RF coverage to clients throughout the upgrade process. Rolling updates support automatic candidate selection using Radio Resource Management, RRM, based AP neighbor information, based upon a chosen percentage per iteration, 5%, 15%, or 25%, with the default being 15%. The wireless controller auto-selects candidate APs to be upgraded in each iteration. Clients from the candidate APs are actively steered away using 802.11v packets with the disassociation imminent field set to help ensure seamless network connectivity as the APs are upgraded. Clients that do not honor this setting are de-authenticated before the AP is reloaded. Support for new AP models using access point device packs, AP DPS. Beginning with the Cisco IOS XE Release 16.11, Cisco Catalyst 9800 series wireless controllers provide a way to support new AP models using AP DPS. This provides a way to introduce new AP models into your network without having to upgrade the wireless controller software version. Also, since the AP DPS are hot patches, they do not require a reload and require no downtime of the wireless controller. The following table summarizes high availability support of the various controllers. Okay, so we just read about these. It looks like we've got two that don't support N1, N+1. And these are the embedded ones, so you can't do N+1 if you have an embedded. Yeah, an embedded, I guess, controller. Yeah, and they can't do lag either. So, okay, so I made it down to the multicast support. I apologize for the audio going out. It's really Was not expecting that to happen. I guess one of the things on my bucket list is to try to make like an actual good like YouTube video where like if it gets a lot of views, goes viral, like that would be a good thing. I think a lot of these are just kind of junk, and to be honest, they're kind of meant to be junk because really it's just meant to kind of force myself into doing something that I consider productive. But at the same time, how productive is it to read a guide like this where I'm really not working with wireless right now, and by the time I am working with wireless, or if I ever do, how useful will it have been to read this? And not only that, as we saw with my study habits going into the JNCIESP, free resources online are hugely lacking, and I was only able to get a 17% out of 100 on a test just using free resources out there. So this guide really is hugely lacking and really doesn't have any relevant information when it comes to practical real world job skills. So that's going to be the end of this video. Sorry for the audio issues again. Next video I'll be starting with the multicast support section.